In this section, we're going to be looking at a summary of curve sketching or graphing a function. We're going to bring together a lot of ideas from pre-calculus, Chapter 1, Chapter 2, and Chapter 3 in order to properly sketch any kind of graph that we are given. So some of the following aspects of functions and graphs we're going to be looking at are going to be X and Y-intercepts from pre-calculus, symmetry, whether a function is even, odd, or neither, domain and range, continuity, or more importantly, where a function is discontinuous, vertical asymptotes, horizontal asymptotes, differentiability, we're going to use this to find critical points of the function, local extrema, increasing, decreasing, concavity, inflection points. And again, the idea of this is to be able to graph a function using the derivative especially. Most of these aspects we're going to be finding using the critical points of the function and the derivative. That's going to be points when the derivative is equal to 0 or does not exist, or when the second derivative is 0 or does not exist. We're really going to think about what the shape of the graph is. So let f be a function defined on some interval a to b, and knowing the sign of the derivative and the second derivative can clue us in on the shape of the graph on that interval. So I have 4 quadrants here, and that's going to look at when a function is increasing and concave up. If it's increasing, we're saying the first derivative is positive. If we're decreasing, we're saying the first derivative is negative. If we are concave up, we are saying the second derivative is positive. Concave down, we're saying the second derivative is negative. And given any point or interval that I know the sign of the first and second derivative, I know the general shape of the graph. So if my function is increasing concave up, I need to go up from left to right in a smiley face fashion. That is going to look like this. From decreasing and concave up, it's going to be like the other half of the smiley face, going down from left to right. If I am increasing and concave down, one half of the frowny face, decreasing and concave down, the other half. These are the 4 general shapes of a graph that I'm going to be using to connect the dots in a specific way. So here's how we're going to do this. We have a step-by-step process on how to sketch a graph. We're going to find a lot of different information, bring it all together. None of these steps are 100% needed at all, but we're just going to go through them in order to sketch the graph. Sometimes we may say that the graph does not have any vertical asymptotes, so it may not be useful. Or, for instance, the range is really difficult to find, so we're not going to deal with it. Maybe symmetry is really just not useful at all in this problem where there is no symmetry, so on and so forth. But the general idea is to get a few points that we know on the graph and then be able to connect the dots in a specific way, knowing the sign of the derivative and the second derivative. So we're going to look at 3 examples in this lecture, going through each of these steps, and then sketching a graph at the end. So, first example, we're going to try to sketch the function x squared plus 1 over x squared minus 4. Now this may be a function that you could actually graph in a pre-calculus course as it's a rational function, but we're going to show how to do it with the derivative and the second derivative. First thing we should do, and this is important for any topic, for any function, is to find the domain. That's a very important one. And when domain, you're thinking of either the denominator being 0, negative under a square root, or dealing with a logarithm, which we haven't introduced yet in this course. In this case, we have a denominator, so if I want to find the domain, I'm going to set the denominator equal to 0. In this case, x squared minus 4 equals 0. Solve for x, and I get x squared equals 4. Let's take the square root of both sides, and I get x equals positive negative 2. So this means that my domain is x not equal to positive negative 2. In interval notation, you could write that in a different way. That's all we would need, is that there's an issue at positive and negative 2. Let's go on. range. In this case, range is going to be difficult to calculate, so we are not going to deal with it. We can see at the end what the range will be, but it's not an easy thing to do for some problems. Some problems it's very easy and it's a good check to make sure we're doing the right thing, not so much in this one. You may be asking, how do I know whether it's easy enough or find the range? There is no clear answer. Sometimes it's just not worth going through that process. None of these steps are 100% needed. That is a big point here. Next, let's find the X-Intercepts. So to find the X-Intercepts, we can set the function equal to 0 and solve for x. And note, when we do this with a rational function, the first step is always going to be to multiply by the denominator. So this will just give me x squared plus 1 equals 0. And it is true that for rational functions, if you want to find the X-Intercepts, you can just set the numerator equal to 0. And these are important points to find. So here we have x squared plus 1 equal to 0. That's going to give me x squared equals negative 1. X equals positive negative square root of negative 1. That is a problem. We can't take the square root of a negative number. That's positive minus I, an imaginary number. And this just means that there are no X-intercepts, which is not a problem. That's all right. Next, let's look at the Y-intercept. There can only be one Y-intercept, otherwise it's not a function. And that's going to be done by plugging in 0 into the function. A nice, easy thing to do most of the time. This will give us negative 1 over 4. Now the reason we have this is that our Y-intercept is going to be the point 0, negative 1/4, and now I have a point on my graph that I can start from. In order to graph any function, it's good to have some points. We're going to try to connect the dots in a particular way. Now let's look at step 5. We're going to look at vertical asymptotes, if there are any. To find vertical asymptotes, we are going to set the denominator equal to 0. And note, this is actually the same thing that we did for the domain. Because vertical asymptotes are domain issues, we're going to get, again, x equals positive negative 2. Okay, vertical asymptotes are lines. We need to write them in a line format. X equals positive negative 2. Next, we're going to look at horizontal asymptotes. This is looking at end behavior, or limits at infinity. All these are the same thing. What happens to the function as we get really big or as we get really small? What's the end of the function look like? So to find this, we can either look at the limit from the left or the right. So let's do both of those. Let's first look at the limit going to the right. And from the last section, section 3.5, we looked at limits at infinity. In this case, the degree is the same on the top and the bottom. So the horizontal asymptote, or the limit, is going to be equal to the ratio of the leading coefficients. In this case, we're going to have that this limit is equal to 1. The coefficient on the x squared is 1 on the top. Coefficient on the x squared is 1 on the bottom. So we just have 1. This means we have a horizontal asymptote of y equals 1. This means that the right end behavior, if you want to write it in a different way, you might have done this in a pre-calc class, right end behavior as x goes to infinity, y goes to 1. Now let's look at the other end behavior, in this case the left end behavior, or the limit as x goes to negative infinity for x squared plus 1 over x squared minus 4. And really it's the exact same thing. We have the exact same reasoning here. And we have that this is equal to 1. Again, it's the same horizontal asymptote. For rational functions, we're not going to have anything different like that. Or we could say that the left end behavior here is as x goes to negative infinity, y goes to 1. So now we know what happens at the end of the graph with those end behaviors. Next thing is sometimes not useful at all. In this case, we're going to look at symmetry. We're thinking about, is this an even function? Is this an odd function? Is this neither? If the answer is neither, this is not helpful at all, but if it's even or odd, we know that the right-hand side of the graph is going to be the same as the left-hand side or opposites of each other. To check for symmetry, let's just review a little bit. If a function is even, that means that f of negative x is equal to f of x. And if it is odd, this means that f of negative x is equal to negative f of x. This is an idea that you may want to review in pre-calculus. So to check for symmetry, what we can do is we can look at just f of negative x and see what pops out. In this case, we have negative x quantity squared plus 1 over negative x quantity squared minus 4. When you square a negative number, it becomes positive. So this is the same as x squared plus 1 over x squared minus 4. And we look at it, and that is the exact same thing as the function itself. So f is even. This means that we are symmetric about the y-axis. All right, so far what we've done is we've just found a bunch of information about this function. We know the domain is all real numbers but positive, negative 2. We know that it doesn't have any x-intercepts. We know one point on the graph, that's this y-intercept, 0, negative 1/4. And we know that at those domain issue, they actually have a vertical asymptote at those points. Then we know that as x gets really big or really small, the function is going to approach the value of 1, and that the function is even, so the right-hand side of the graph should be the same as the left-hand side of the graph. But there's more to do than that. Now we're going to think about the shape of the graph, and to do that, we're going to find the critical points of the function and the derivative. So step 8 here, we are going to find when the derivative is equal to 0 or does not exist. So we need to find the derivative here. To do this, we are going to need to find derivative of x squared plus 1 over x squared minus 4. We need to use the quotient rule. So this is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So this is going to give us the derivative of x squared plus 1 is 2x times x squared minus 4 minus x squared plus 1 times the derivative of x squared minus 4, which is 2x, all over x squared minus 4 squared. Let's do some algebra to make sure this is a little bit neater. This is going to give us 2x cubed minus 8x minus 2x cubed minus 2x, distributing that negative. I'm going to leave this x squared minus 4 squared as is, as we're not going to deal with it that much. We're thinking about finding critical points. And this will be the 2x cubes cancel out, and we are left with negative 10x all over x squared minus 4 squared. So that's our derivative. We want to find when is this derivative equal to 0. That's going to be when negative 10x is equal to 0, or at the point x equals 0. And we also want to find when does this derivative not exist. And that's going to be when x squared minus 4 equals 0, or x equals positive negative 2. Those are special points that we need to consider. All right, and these are review from previous section. Critical points of f. Step 9 says that we're going to do a similar sort of thing, except this time we're going to look at the critical points of the derivative, the second derivative, equal to 0 or does not exist. So, first step is I need to find the derivative of the derivative. So we're going to find the derivative of negative 10x over x squared minus 4 squared. And again, we need to use the quotient rule. So let's go through it. This is going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. It's going to look gross, but it's going to be just x squared minus 4 squared squared, which is x squared minus 4 to the 4th. This will give us a derivative of negative 10 x squared minus 4 quantity squared plus 10x times the derivative of that, which is 2 times x squared minus 4 times 2x, the derivative of the inside. That's using the chain rule there. All over x squared minus 4 to the 4th. And let's do a little bit of cleaning up here. We have an x squared minus 4 in every single term. We can write this as negative 10 x squared plus 40 plus 40 x squared all over x squared minus 4 to the 3rd power, or 30 x squared plus 40 x squared minus 4th to the 3rd. So if I want to find the critical points, I'm going to set this equal to 0. That's going to give me 30x squared equals negative 40. That's going to be x squared equals negative 4/3. And this just means that we have no points here, as we can't take the square root of a negative number. When does the second derivative not exist? Well, again, that's going to be when x squared minus 4 is equal to 0. That's, again, our special points, positive, negative 2. So here are my critical points of the derivative. Now that's a lot of work to find the derivative and second derivative, but we now have that. We have some information from before, and we know that there are special points 0 and positive, negative 2, which the shape of the graph could change there. Either it could change from increasing to decreasing, or from concave up to concave down, or vice versa, and that's going to give us the shape of the graph. We're going to see that on the next page here. So here's how we're going to deal with all that information and be able to bring it in to a graph of the function. Here I have 3 axes. I have the xy axis, the function itself on the bottom. I have the derivative on top of that, and the second derivative. And we're going to use this information to find the shape of the graph, finding and testing points on the interval. So for the second derivative, I'm going to be looking at the points x equals negative 2 and x equals 2. That's my critical points of the derivative from the previous page. For the derivative, I'm going to be looking at that negative 2 and 2, and also 0. Those were the critical points of the function. And now I'm going to also just input some other information that I have from the previous pages. So, for instance, I know that at negative 2 and 2, I have a vertical asymptote. So I'm going to draw those in right now. And the nice thing about having the axes there is I'm actually going to draw those in the entire way up. I know that there's a division between negative 2 and 2 that I need to worry about. I know that there was a horizontal asymptote at y equals 1. So I'm going to draw that horizontal asymptote. It only matters at the end of the function, not anything in the middle. I know that there is a y-intercept of negative 1/4. This is the point 0, negative 1/4. I know that there is no x-intercepts, and I know that the function is even, so it's going to be symmetric about the y-axis. All right, so as we go through this, I care about the sign of the derivative and the second derivative. So I'm going to test points in here. For the second derivative, let's test negative 3, 0, and 3. Let's not do anything crazy. Let's test that into the second derivative. So I'm going to look at f double prime of negative 3. That's going to give me, it's going to give me 30 times negative 3 squared plus 40 all over x squared minus, sorry, not x squared, negative 3 squared minus 4 cubed. What I care about is the sign here. It's clear from the top I have a positive 9 times 30 plus 40. That's going to give me a positive on the top. And on the bottom I have 9 minus 4 is a positive number. When I cube it, that's a positive number. So this is going to be positive here. When I test that for 0, we're going to have 30 times 0 squared plus 40 all over 0 squared minus 4 cubed. On the top, we have a positive 40, positive number. On the bottom, we have a negative 4 cubed. That's going to be a negative number. Positive over a negative is a negative. So everything on the interval from negative 2 to 2 will have negative second derivative, so it's going to be concave down on that interval. And finally, f double prime of 3. We already know it's going to be positive because of our symmetry, but we could also find it the same way. 33 squared plus 40, 3 squared minus 4 cubed. This is going to give us a positive over a positive. That's a positive number. All right, let's do the same thing with the derivative. I'm going to test 4 points here. Negative 3, negative 1, 1, and 3. So here we go. We got f prime of negative 3 is going to be negative 10 times negative 3, negative 3 squared minus 4 squared. If you square something, the answer is always going to be positive, so the bottom is positive, and the top is also positive, giving us a positive number. Let's do the same thing for negative 1. We just said that the bottom is always going to be positive. It's a squared number. And on the top is going to give us a positive number, a negative times a negative. Again, a positive thing. All right, let's do it for f prime of 1. That's going to give us a negative number on the top and a positive number on the bottom, as always. That's going to give us a negative. And f prime of 3, same thing, a negative on the top, positive on the bottom will give us a negative. So we now know that at negative 2 and 2, those are going to be points where the concavity changes. That's going to be an inflection point, although it's not really a point of our function, so it's not going to be considered an inflection point, just a point where it changes the concavity. And we know that 0 is going to be a local min or local max because it changes from increasing, decreasing, and the first derivative test tells us that 0 is going to be a local max. More information to graph the function. So now we have everything we need. We have this chart on the left-hand side here. It's going to tell us everything we need to graph this function. On the interval negative infinity to negative 2, I know that this is going to be concave up and increasing, second derivative positive, first derivative positive. And the only way to draw that, taking care of these asymptotes, is going to be as follows. It's going to be like this. It approaches that line y equals 1 as we go out, and it has to approach the asymptote, never actually get there. It's the only way to be concave up and increasing. We know this function is symmetric, so actually it's going to be the exact same thing on the opposite side. Let's see if it actually works out. This is concave up, and decreasing, and that will be as follows, that other half of the smiley face. Then on the interval from -2 to 0, we know it's going to be concave down and increasing, and it has to go through that special point, that Y-intercept, 0, -1/4. The only way for that to happen is we need to approach this asymptote. It's going to be like this. Again, since this is symmetric, it has to be the same on the other side, and we can verify on the interval from 0 to 2, it has to be concave down and decreasing, and that works out. And this is a pretty good sketch of our function. We can double check this with some kind of online graphing calculator if we're not sure, but this is good. Let's move on to the next example. We're going to do this 2 more times with different kind of functions and see what changes from function to function. All right, so here we're going to look at the function x times square root of 4 minus x. Let's start with domain. In this case, there's no denominator, but I do need that the stuff inside the square root has to be greater than or equal to 0. We can't have a negative in the square root. So solving this little equation, we get 4 is greater than or equal to x, or we can write that as x is less than or equal to 4. Here is our domain. We could write that as -infinity to 4 in brackets. Once again, thinking about the range, if we plug in values less than 4, the x is going to make them negative if we plug in negative numbers, and the square root is not going to affect it that much. That's just going to mean we're going to be going down to -infinity. How high we can go is a little bit difficult to calculate, and again, we're not going to calculate the range here. It is difficult to calculate. Let's move on. We'll think about X-intercepts now. It's going to be setting the function equal to 0 and seeing what we get out. So here we go. We have f of x equals x square root of 4 minus x equal to 0. And I want to solve for x. To get rid of the square root, let's square both sides. That's going to give us x squared times 4 minus x equals 0, or 4x squared. Nope, don't need to do that even. From here we have that x is equal to 0 and x is equal to 4. Our x-intercepts are going to be the points 0, 0, and 4, 0. Let's find the y-intercept. Again, to find this, we are going to plug in 0 to the function. And this will just give us 0. And again, we sort of already found that, as we know that x equals 0 is an x-intercept, so the origin is also going to be a y-intercept as well. Okay, we could think about the vertical asymptotes, but since there is no denominator, there are no vertical asymptotes. I'll abbreviate that VA, no vertical asymptotes. Next, we're going to think about the limits at infinity, the end behaviors. So let's look at when the limit approaches infinity of the function. But let's note that this doesn't make any sense for this function. Because our domain is negative infinity to 4, so we can't let x get bigger. Let's look at the other end behavior, that one we can work with. Here we can kind of try to plug in negative infinity. We're going to have negative infinity times square root of 4 minus negative infinity. We're going to do some really bad illegal algebra here. Put it in quotation marks, so we're okay. It's going to be negative infinity times 4 plus infinity. This will just give us negative infinity times infinity is just going to be a negative infinity. So as x goes to infinity, y goes to negative infinity. Let's think about any symmetry. This question helped us out in the last example. It may not help us out in this one. We're going to look at f of negative x. It's going to be negative x times 4 minus negative x. It's going to give us negative x times 4 plus x, and that is not equal to the original function, and it's not equal to negative the original function. So there is no symmetry here. It's not going to be symmetric about the origin or the y-axis. Not odd, not even. All right, let's continue. Now we're going to look at critical points. So we're going to find the critical points of f. And that is setting the derivative equal to 0 or finding when it does not exist. So here we need to find the derivative. Derivative of x times square root of 4 minus x. And here I need the product rule. So this is going to be equal to the derivative of the first function, x, times the second function, square root of 4 minus x, plus the first function, times the derivative of the second function, derivative of 4 minus x, which will give us derivative of x is 1, so this will just be 1 times square root of 4 minus x, plus x times the derivative of square root of 4 minus x using the chain rule. This will give us a 1/2 4 minus x to the negative 1/2 times a negative 1. Remember that we have that square root of 4 minus x. We could rewrite as 4 minus x to the 1/2 power. Simplifying this derivative, this is going to give us the square root of 4 minus x minus 1/2 x 4 minus x to the negative 1/2. Or we could write that as square root of 4 minus x minus x over 2 square root of 4 minus x. Whether that's the easiest way of writing it or not, who knows? Let's actually combine this into one fraction. I think that might be a nice thing to do. Multiply the top by 2 square root of 4 minus x. This is going to give us square root of 4 minus x times 2 square root of 4 minus x over 2 square root of 4 minus x minus x over 2 square root of 4 minus x will give us a 2 times 4 minus x over 2 square root of 4 minus x, which will be 8 minus 3x over 2 times square root of 4 minus x. So I want to find when is the derivative equal to 0. That's going to be when 8 minus 3x is equal to 0. That's going to be 8 equals 3x, or x equals 8 thirds. We also need to think about when is the derivative not exist. That's going to be when 2 square root of 4 minus x equals 0. That's going to be when 4 minus x equals 0, or when x equals 4. And there are my critical points. Note that the derivative also doesn't exist. I should make a note here. So the derivative also does not exist on the interval 4 to infinity, but this is not in the domain, so we don't care. However, that point x equals 4 was in the domain, so we worried about it. In the previous problem, we had critical points of positive, negative 2. Those were also not in the domain, but they were important because they were within points that are also part of the domain. 4 to infinity is not anything about that. Part 9 here, we're going to find the critical points of the derivative. That's going to be when the second derivative is 0. And again, I need to find the second derivative. So that is going to be the derivative of 8 minus 3x over 2 square root of 4 minus x. And in this case, we need the quotient rule. So I'm going to take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Which gives us a nice thing as we have a square root being squared. Anyways, we have the derivative of 8 minus 3x is negative 3 times 2 square root of 4 minus x minus 8 minus 3x times the derivative of 2 times square root of 4 minus x, which is going to be a 1 over negative 1 over square root of 4 minus x. Using the chain rule, the 2's are going to cancel out with a 1/2 power all over 4 times 4 minus x. I want to find when is this equal to 0. So to do that, I am not going to worry about the denominator. That's just going to give me a -6 square root of 4 minus x minus this plus this 8 minus 3x over square root of 4 minus x equal to 0. We can multiply by square root of 4 minus x. And this will give me a -6 times 4 minus x, and I multiply by square root of 4 minus x, plus 8 minus 3x equals 0. Or -24 plus 6x plus 8 minus 3x equals 0. So give us a 3x minus 16 equals 0. 3x equals 16, x equals 16 thirds. That's one of our critical points. And again, we have when is the second derivative not exist. That's going to be at the point x equals 4. So that is also a critical point. All right, so now we're going to bring in all this information. Let's go back to the previous page real quick, and we have the domain is just going to be -infinity to 4. We have two X-intercepts at 0 and 4, with a Y-intercept there too. No vertical asymptotes. Left end behavior going down to -infinity. No symmetry. We have critical points at 4 and 8/3, and critical points of the derivative at 4 and 16/3. Let's put this all together in this chart. So we have critical points of the derivative first. X equals 4 and x equals 16/3. And if you caught it already, fantastic, but 16/3 is not in the domain. So it is not a critical point. Even though we found it, we have to be careful of when is it actually in the domain. So our only critical point here is 4. I only care about one side of it because I don't care about the whole right side of the function. For the derivative, for the critical points of the function, we have x equals 4 and x equals 8/3, which is a little bit less than 3. So here we have 8/3 and 4. And we have 3 points that we need to test. So let's do that first. I guess we can label our X-intercepts and Y-intercepts. We have X-intercepts at 4, 0 and 0, 0. And we don't really have any other information other than the domain is just going to be to the left of 4. So let's check the critical points. So first of all, let's check a nice easy point for the second derivative, 0. And for the first derivative, we'll check 0 and 3. So second derivative, this will give us negative 6 square root of 4 minus 0 minus 8 minus 3 times 0 times negative 1 over square root of 4 minus 0 all over 4 times 4 minus 0. That looks gross, but again, all I care about is the sign, whether it's positive or negative. We know that the denominator is going to be positive, and the numerator is going to be negative 6 times square root of 4 minus something that is going to be positive. So this is going to be a negative number on the top. This whole thing is negative on the entire function, always concave down. Let's check the 2 points for the derivative. F prime of 0, 8 minus 3 times 0 over square root of 4 minus 0 times 2 here. And this will give us a positive number on the top, positive number on the bottom. That is positive. And f prime of 3 will give us an 8 minus 3 times 3, 2 square root of 4 minus 3. That is a positive on the bottom, negative on the top. We have a negative on that interval. So this means that we have a local max as we go from increasing to decreasing at x equals 8/3. Okay, if we plug in f of 8/3, this is going to give us 8/3 times square root of 4 minus 8/3. This is going to be about 3.07 if we plug it into a calculator. A little bit more than 3. So this gives us another point on our graph, 8/3, a little bit more than 3. And I know that this is going to be concave down always. We need to go through those 3 points, and it's going to be increasing, change to decreasing. I need to go down to negative infinity on the left. This is going to look like this. This is hitting the function. There we go. That is our entire function. There's nothing to the right of 4, so that's our whole thing. Always concave down, switches from increasing to decreasing. All right, and we're going to do this one last time. Here we have the function 3x to the 4th plus 4x cubed. Let's think about first the domain. And there's no denominator, there's no square root, there's no logarithm. This is going to be all real numbers. No issue there. Let's think about the range. And again, it's going to be all real numbers here. Or possibly not. It's 3x to the 4th. So for the range, it's also, again, difficult to calculate. We do know that as x goes to infinity, y is going to go to infinity. It's going to be unbounded on the top, but it's not so clear on the bottom. As we plug in bigger or smaller numbers, the 3x to the 4th is going to dominate. This is going to be some finite number to infinity. I think we found that the range is not super important to calculate. For most functions. It would just be a check as to make sure we're doing things right as we go through the other steps. Anyways, here we go. X-intercepts. We're going to set the function equal to 0. And we're going to factor that. We can take out an x cubed. We left with a 3x plus 4. This will give us x equals 0 and x equals negative 4/3. So we have x-intercepts of, again, the origin and negative 4/3, comma 0. Let's think about the y-intercept. Here we're going to be plugging in 0 into the function. And again, this gives us 0, and that's not a surprise, as we kind of already knew that the origin was the x-intercept. It also has to be the y-intercept. Let's think about vertical asymptotes. There are none. There is no denominator. Now let's think about the end behaviors, the limits at infinity, the horizontal asymptotes if there are any. We're going to look at the limit as x approaches infinity, 3x to the fourth plus 4x cubed, and as x gets big, that's just going to blow up to infinity. For the other side here, limit as x goes to negative infinity, we can just look at just the dominating term. This is going to be equal to the limit of the 3x to the fourth. And that's going to give us 3 times negative infinity to the fourth, in quotes. This will give us, again, positive infinity. So we could say, as x goes to infinity, or x goes to negative infinity, y goes to infinity. Let's take a second and think about symmetry, as it would be nice if it is symmetric. We're going to look at f of negative x, 3 negative x to the fourth plus 4 negative x cubed will give us 3x to the fourth minus 4x cubed, which is not equal to the function. It's also not equal to negative the function. There is no symmetry here. All right. Next, we're going to look at the critical points. Of f. Again, that's finding when the derivative is equal to 0 or does not exist. So I need to find the derivative of 3x to the fourth plus 4x cubed, which will be 12x cubed plus 12x squared. And we are going to set this equal to 0. We can factor out a 12x squared, left with an x plus 1. And this gives us two critical points, x equals 0 and -1. We also need to consider when does the derivative not exist. But since this is a polynomial, there's no issue here. So we have x equals 0 and 1 are the critical points. We're then going to do the same thing for the derivative. That's finding when the second derivative is 0 or does not exist. Here we're going to look at the derivative of the derivative. So the derivative of 12x cubed plus 12x squared will be 36x squared plus 24x. We are going to set that equal to 0. We can factor out a 12x again, leaving us with 3x plus 2. And this gives us x equals 0 and x equals -2/3. Once again, we should think about when the second derivative does not exist. Again, we have a polynomial, so this is going to be nowhere. All right, let's bring everything together here. We have the critical points f prime, where x equals 0 and x equals -2/3. So let's label that 0 and -2/3. And we had our critical points of f, x equals 0 and x equals -1. And we had x-intercepts of 0 and -4/3. Good place to start. We need to connect those dots in a certain way, and we know that -1 and -2/3 are going to be important points in that. So let's get to it. We need to test some points here. We need to test 1, something in between 0 and -2/3. How about -1/3? And how about -1 on the other side? And for the derivative, we'll test -2. How about a -1/2? And 1 for the derivative. So let's get to it. We need to plug in into the second derivative. -1, -1/3, and 1. And we're going to plug that into the factored form, 12x times 3x plus 2. This is going to give us a negative number times a negative number. For the -1/3, this is going to give us a negative number times a positive number. And here a positive number times a positive number. It's going to give us positive, negative, positive. And our three regions there for the second derivative. For the first derivative, we're going to look at f prime of -2, f prime of -1/2, f prime of 1. Remember that our derivative is 12x squared times x plus 1 Plugging this in, we're going to have a positive number for the first one always because of the x squared. And for the second coordinate, it's going to be negative, positive, and positive. So this is going to be a negative number, positive number, positive number. So this means that we have a local min at x equals -1. And we can actually find what value that's going to be pretty easily. F of -1 is going to be 3 times -1 to the 4th. 4 times -1 cubed will give us a 3 minus 4, -1. Then at -2/3, we have a inflection point. And at x equals 0, the concavity changes at that point. So here's going to be a lesson in connecting the dots in a certain way. From the interval -infinity to -1, we are going to be decreasing and concave up. So from -infinity to -1, I'm going to be concave up, decreasing. I need to go out to infinity as x gets smaller. So this is going to look something like this. Then from -1 to -1/3, we're going to be -2/3. Sorry, from -1 to -2/3, we're going to be concave up and increasing. Then we're going to shift to concave down for a little bit here, all the way to 0. And then we're going to shift back to concave up and increasing. For the rest of this function. If I would zoom in on that last little bit, here's -1, here's -2/3, here's -4/3, here's 0, x-intercept at -4, x-intercept at 0. We have a y-intercept down here at -1, or a local min at -1, -1. And we know it's going to change concavity here. This is going to look like this. Concave up, shift to concave down, back to concave up. So this is concave up. And this section is concave down. It's subtle, but there is a difference in those points. We can see it a little bit in our small graph, but if we do zoom in, it's a little bit easier to see. So remember that the purpose of this section is to bring in a lot of different aspects. Some are important, some are not important for different functions, to be able to get a good graph of the function. In each of our 3 examples, we're able to get a fairly accurate drawing of our 3 functions using this element of graph sketching or curve sketching.